In this slide, we have an example 13.2, to show how we calculate the estimation of errors with the formulation that we showed in the previous slide, the correlation coefficient basically. We have the same data here, you can see 7 data from the first example 13.1 and the y values as well. So because we need to have the difference of the data from the mean, basically we calculated mean before and we subtract this from the mean and get the values. We need this. Also we will need the difference of data from the regression line predictions. We predict the regression, actually A0 and A1, we found these in 13.1, example 13.1. We use them here and get a value for this and subtract them from the yi to get the values. So we will use this to be able to obtain the results. And our actually formulation was, if you remember, r square is equivalent to st minus sr divided by st. You can use this formulation. For this, we need to calculate st and sr values. But first, before this, it says let's calculate the standard deviation. So first we need to calculate the standard deviation. Let's say A. And standard deviation is st divided by n minus 1. Also we will have syx. After regression, we will have sr divided by n minus 2. Let's calculate these two. And we know that st is, this st is basically the total of y minus y mean, yi minus y mean square. So these, we will get the square of these. Actually, this is the square. Maybe there is a wrong statement here. Let's write it here. This is the square. Keep this in mind. So these are the square values of them, and this is the summation. So this st is this actually. This is st. Similarly, sr is the summation of these regression line subtracted from the yi. So this is sr. Let's write this correctly. This is st and this is sr. Then we can use these in here to calculate these. Sy is equivalent to root square 22.7143 divided by n minus 1. 7 minus 1 is equivalent to 1.9457. Also, syx is equivalent to 2.9911 divided by 7 minus 2. And this is 0.7735. Okay, we calculated them. And you can see here that syx is smaller than sy, which means we have a good regression. Actually, the linear regression has merit on fitting the data. So the decrease of the standard deviation is a good thing actually for regression. Okay, now for B, we are using standard error of estimate. Actually, we already calculated it. Standard error of estimate is this summation and this one. You can see that the standard error of estimate is also reducing from 22 to 2, which means we have a good improvement here as well. So if we want to correct, actually A is just the standard deviation, this one. B is standard error of estimate, this one, syx. So let's write correctly. This is B. So this is A and this is B. And we compare the results of A and B. Now we will go to C. C is the correlation coefficient. And for the correlation coefficient, we have this formulation. This is C actually. Let's write C here. And for that, simply we already found ST and SR. So R square is equivalent to ST is 22.7143 minus SR is 2.9911 divided by ST 22.7143. And the result here is 0.868. We can also calculate R by taking the root square of R square, which is equivalent to root square of 0.868. That gives us 0.932. So if the R square is smaller than 1, the R will be larger than R square. You can see here because we are taking the root of it. And you can see that R is getting close to 1. And this is also close to 1 as well, which means that this linear regression is a good fit. And it indicates that it means 86.8%. So if we multiply this by 100, this gives us an coverage value, 86.8% of the original uncertainty has been explained or covered, let's say, by the linear model, linear regression model. Is this good? Well, it depends. Because it's close to 1, we can say it's good, but we can also ask that is there any better fitting processes to this? Maybe a polynomial line can be a better process. I mean, a second order regression. We will talk about that in the next chapter. But for now, this looks good. If you have only like linear regression option, then you can say that this is good because there is no other linear regression line alternative to this. This is the only alternative that you can fit because the least squares gives only one alternative. That's the best fit to the data in the linear sense. And this looks good actually.